And in the mid-90s, I took telecommunications engineering from UC Berkeley. Oops. Just lost your guts. And put it in the pocket. There you go. And I was hoping to find the textbook for digital telecommunications that we used then. I couldn't. I don't know what I did with it.
Burned it.
Yeah. But that's pretty old stuff. So I had to start all over again and do a whole bunch of research. And it was pretty interesting. Oh, I got to turn this back on again. So the question is, how do we get from what's coming out of your mouth to the ones and the zeros? I mean, so far all of the speakers have talked about addressing how the high-level stuff works. And we really need to understand how this lower-level stuff works, particularly for voice, and how we got there. And then it has to go back again. But what that magic tool is called a vocoder. And vocoder is short for voice encoder. And in the mid-90s, when they taught me about this, I thought this was relatively new. Turns out it wasn't. So let's start out with a bit of history first. And this is really where it started. This guy, Homer Dudley, in 1928 at Bell Labs, they started looking at, well, let's look at the human voice and the structure of what's in your face and in your head that actually makes those sounds. And so they looked at, well, we've got amplitude, we've got start and stop of amplitude, we've got a frequency, we've also got some carrier. In other words, what you breathe in and out is the carrier for that. And so how do we duplicate that? Somehow we have to figure out, we can't just record it in analog, we've got to put it on some sort of medium. So this is what he came up with, and this is what they showed at the World's Fair in 1939 and 40. And what's interesting about that is that it speaks into the microphone, and they split it up into a bunch of different frequencies. They do a bunch of filters. They've got down here where they got buzz and hiss and pitch bias, and then they send it out in parallel. And they call this a continuous wave sort of transmission. And then it comes out the loudspeaker at the other end. And this is the boost they had at the World's Fair. Here's the vocoder. And then this thing called the VODER, V-O-D-E-R. And when you look back at this picture, this is the VODER part. Once they figured out how to put it in, they had to figure out how to get it out. And how do we do that? So they had this is the interesting part of the VODER. They had this woman down here with 10 finger keys, a foot pedal, and a wrist thing. And she spent a whole year learning how to operate this so that it could actually mimic the human voice. And it wasn't easy. Here's a YouTube link. I'm not going to show it now because we're running short of time. And I really suggest that you listen to that because it's pretty interesting. Because the voice that comes out of it really sounds funny. But here she is. She's got 10 keys that she's tickling. She's got a wrist bar that comes down here to do the pitch bias and buzz and a hiss. They had two vacuum tubes, one that would produce the noise of the buzz and one that would produce the noise of the hiss. And they used that in conjunction with the foot pedal to kind of modulate the hiss and the buzz to actually create the sound. And the next thing that came up was this thing called the Sig Sally. And this is prior to World War II. And what this did was took some of those concepts and expounded upon them. This is a big device, and they used this. The first use of this was President Roosevelt talking to Winston Churchill for really high security communications. But you have to look at, well, we're going to sample this in analog, but there's all kinds of stuff because John sounds different than me, Carl sounds different than me, And DES is really quite a bit different. So how do we characterize those? And so they came up with this kind of list. I added this last one, music kind of singing, because some voices are kind of melodic, different than what my voice might be. So how often do we got to sample that? How do we decide what we do to make that sampling to be able to change that from a continuous wave that came out of Homer Dudley's work? And so this is what they did. This is the first one. This is 1939 patent. I looked at a lot of patent documents. And so what they did, as you can see here, they got 0 to 230, 230 to 550. So they filtered this out, and each one of these is a separate signal. And it's kind of like that original picture I showed you with all those lines where they had actually 12 different ones. And then they had to figure out, well, with the amplitude, we've got to cut that off somewhere because this is all relay circuits. So when do we turn the circuit on and let energy go through, and when do we turn it off? And that they called a mark was it's on and a space is it's off. Essentially the original 1 and 0. And then they had some variable gain. There's another patent that was the first automatic volume control prior to this, which was kind of interesting. But this is what founded that Sig Sally machine. Notice the patent date on it. 1976. That patent was originally filed in 1941. And they kept it secret all those years. But notice that they've got a lot more, finer split on the frequencies that they split it out. And this is continuous wave. The other part of it that's really interesting is you note down here we've got 12 different output signals. And remember the vocoder, she had 10 keys, a foot pedal, and a wrist pad. Adds up to 12, doesn't it? Most days. And they sent that by individual radio frequencies. This is the first use of spread spectrum radio. This is where it happened. So they spread that over a bunch of different frequencies, and you've got marks and spaces at each different frequency, and so that was really hard to break. Now the other part of it, here's the receive side. Let me go back here for a second. These are actually tapes. And what they did was to record that on a paper tape. When the Sig Sally was made, it was on a 14-inch disc, record disc, that they had two of those devices that were synchronized, and they could do 10 minutes of code with it. And to transmit, that was the key. Let me show you. Where am I going? Wrong way. So what they did, if you look at this, this is the actual wave of the speech. And they had a key, and that disc or the paper tape had the key. And so they combined the actual voice with the key, and then they sent it. So that was encoding it. But the other part of it is if you look at this recreation, notice how different this line is from the original signal. So it sounded really, really funny. And that was an artifact of we're using relay circuits and just looking at ons and off, and we split it up into different frequencies. And it took them a while to train the users to understand that who that is, and that voice sounds a little different. So then we start talking about sampling, because I want to change this continuous time signal to a discrete time signal. And how many know who Mr. Nyquist is, or Claude Shannon, or Harry Nyquist? Yeah. If you don't know, what are you doing here? Anyway, they started this sampling thing. And the theorem was that if you've got a function x and you limit the bandwidth, we're going to sample it at twice the bandwidth. And so for a voice communication, this is another graph that shows that we're going to sample it, we're going to 16 points and say this is 1 second. And we're going to sample at all of these different locations so we can rebuild that signal pretty good. And we're still using this today. The problem is, with the Nyquist Shannon, that's a lot, oops, wrong way. You know, we got a lot of bits, so can we cut that down? Do we have to do 16? Can we do less and still get the same intelligibility out of the signal? And they said, kind of yes. And so the original PCM that Bell came up with that they used in their phone system only had 8 sample points. And part of that is because the electronics that they had at the time, that's the fastest it could go. Because when they first did it, it was still all vacuum tubes in the early 50s and late 50s. They didn't have the transistor yet, and they didn't have the fast switching networks. And so 8 bits. So if we do the math, if you're sampling at 8,000 times a second and you've got 8 bits, you end up with this 64 kilobit voice channel. And that's been pretty standard throughout the ages, and we still use it today, more or less. However, I think they've done a lot more on compression. But if we want to reduce that, what do we got to do? If that's a bandwidth hog, what can we alter? Can we alter the Nyquist theory? Can we sample it less? You know, frequency? Maybe what we can do is look at, can we reduce the number of sample points? And that's what they did. Differential pulse code modulation. Instead of going back to 0 again, let's just look at what the last bits are and follow that along. Did it go up or down? And we're going to only transmit the difference from the previous sample. So it's only 2 bits. Did it go up or did it go down? And follow that along. And this is where that started in 1950. Now, the part of the reason of trying to get fewer bits is copper's expensive, and that's what they were using at the time. And we need to put more and more voice channels because we got more and more people talking on the phone. And how are we going to do it? This was one way to do it. The other part is if you're not on copper, if you're on wireless, you've got bandwidth issues on wireless as well. So here's some of the elements. You approximate it in a series of segments. Each segment is compared to the previous bits to try and decide, well, where's that curve going? Is it going up or down? And there's some error or latency in that. But to really make it sound good, they found that they had to sample it more frequently. And at that time, they had the electronics to be able to up the sample rate significantly enough so that it was still intelligible. And here's another one, adaptive delta modulation. This is a little different take on the differential modulation. The step size in the previous one was not fixed, and so this is that step size floats. This is what NASA was using, I think it's still using for communication to some of the satellites. Anybody know any different? Or to the space station? I think they're still using that. Now I want to change direction a little bit. I want to talk about the 7-layer model for a minute. How many people have seen this before? Yeah. So the vocoder really exists up here at the application. That's it. And so the stack has to transmit that data down to where it comes out to the radio frequency, and the coding and modulation and error correction is all down there at the physical level. So here's how people know how to define the layer. You really define the interface between the layers. And there's this infamous guy called Pavlovsky, and he was one of the original inventors of the ARPANET. And his rule was, say, if you know what you're doing, you can do it in 3 layers. If you don't, 17 won't help. But the interesting thing is, when we think about what we're doing with our DMR radios, is that the radio to the site, you only look at the data link layer. And then once you get to here, then it has to start looking at the addressing, and that's what Mike talked about. That's a lot about what Doug talked about, was the addressing. And so the radio at the tower where you connect to, it goes up here to the network layer and starts looking at the addressing information. Am I not correct? And then that sends to where it goes, because that's a routing function. Whereas this is really station to station. They just look at the MAC addresses and say, this is the station it's going to. But that's important, because when we get to this, a lot of this is based on understanding that. This is the standard that Tristan talked about, and it was fun reading. I haven't read every single word, but I've looked through a lot of it. But notice here, this is out of that document. Well, what's going on here? They're really only talking about 3 layers, aren't they? Pawlowski's rule really fits, doesn't it? But notice how they split it up, control plane and user plane. This is where all of the call control stuff comes. This is where Tristan's data stuff ends up. It doesn't go over here. Now, the interesting thing about this standard, which blew me away, kinda, is that the vocoder is not included in the standard. And I think that was because the vendors, didn't want to, they wanted to have their own proprietary radios. Like System Confusion won't talk to D-Star. D-Star won't talk to DMR. And that's this artifact. But in the end, they all used the same vocoder. Did I miss a slide here? No, I didn't. It's further down. But then there's all these standards. And I love standards because there's so many to choose from. Which one are you going to choose? And notice there's 4 of them here. I think there's a couple other. This is an interesting one because that's an actual vocoder description. And that vocoder description is actually a proprietary chip. It spells out a particular manufacturer of chip that's the vocoder, and that's that advanced multiband excitement vocoder. And Dean was quizzing me about it. I didn't really dig into that one too much. Project 25 specifies that chip. That's that one standard. And I think that chip it will actually do quite a bit if you tell it, well, which one do I want to use for which application? And everybody's using that chip from this DSP Innovations company. There's some licensing issues. There's some proprietary issues about that. And reading on some of it, some of the people were complaining about the license fees for using that chip or the algorithms. But then they went back to this. 16, it's a linear PCM, linear pulse code modulation scheme with 16 sample bits. Now we've got electronics that are fast enough to be able to do that, and we've got enough memory and coding space to be able to have that many bits to define it. So we talked about the historical beginnings, and I thought that was when I got into it, I thought that was really interesting to see how they got to it and how early they started down it and started to define, well, how are we going to make this happen? Then the other interesting part was in World War II, when they split that up on that Sig Sally and really created spread spectrum radio, because they spread that channel over a wide bandwidth of radio frequencies. And think about how hard that would be able to break. The other part of that is when the keys were on a disc, 14-inch disc. And so when they created the key, they had to copy that disc. There was 2 turntables at each end. And so they had to make that disc, put it in someone's briefcase, and send him and the disc to the other end where the message was going to go so that they could decode it. That was really efficient. But they really didn't have any other way to do it. We're doing paper tapes, and that was, a little more difficult. What? Yeah. And so I talked about the 7-layer model. I talk about some standards or not, because I love standards. I work with standards in the traffic signal world. And the manufacturers, they love standards, but they had to have their own open so that they could make it proprietary. So there really was no standard at all. So I got questions now. Was that clear? Did everybody get something out of that that they didn't know when they walked in this room today? Questions on the internet? Ooh. That's all I have for you. Hopefully it was interesting.
I'll pitch a question. They can have a mic.
Uh-oh, I'm in trouble now.
Don't worry, probably not a hard one, but okay, so in computer science, sometimes we save the results, sometimes we want to save the instructions, right? Like, so we have vector graphics, those are the instructions to make a certain image, or we could just, store the bitmap information.
Or you could store the vector, or you could store the bitmap.
Right, and then like on sound, we could pass around PCM WAV files, MP3s, or we can send around the MIDI files that describe what the instruments are doing to make that sound. So would you describe the vocoder as sort of like MIDI for the human mouth and vocal tract?
Yeah, that's kind of it. The other interesting thing is the VODER. The VODER was really a precursor to Robert Moog and Wendy Carlos's synthesizer. That they kind of took their inspiration from that. And if you listen to that, and I suppose we could play it, we got time now. We should play it. Yeah. Yeah. Now I got to be able to look around to see where I'm at. Come on. Where's my mouse? There we go. Oops. I need to be returned for regrouping. And if you look for this, there's a guy that rebuilt one to try and emulate what this was to understand, because there's nothing left of what they did.
There are 10 filter circuits in the VODER, and combined with the two energy sources, they give a total of 20 separate components to be used in building up speech sounds. But now let's have Mr. Garrett and Miss Harper actually show us what the VODER can do with these 20 separate sounds.
Well, we heard the VODER make a word, and by combining words, of course, we get a sentence. For example, Helen, will you have the VODER say, "She saw me"? That sounded awfully flat. How about a little expression? Say the sentence in answer to these questions. Who saw you?
She saw me.
Who did you see?
She saw me.
How did she see you or hear you?
She saw me.
Now, so far, you have only heard the VODER speak in one voice. But the VODER has other voices which you can use when Miss Harper makes a simple adjustment in his mechanism. Helen, will you have the VODER say, "Greetings, everybody"?
Greetings, everybody.
Now, will you have him repeat that in a high voice?
Greetings, everybody.
And now in his best bass.
Greetings, everybody.
When a boy's voice changes, he's never quite sure whether it's going to be a tenor or a bass. And the VODER, being still a comparatively young man, also has his moments of uncertainty. Let's hear him recite, "Mary Had a Little Lamb."
Mary had a little lamb. This is so wonderful.
Gosh, VODER, you sounded awfully dismal. Snap out of it. Let's hear you laugh.
Okay.
A minute ago, I said the VODER was still a comparatively young man. But that last laugh of his makes me wonder whether I might not have been wrong. Do you really feel as old as you sound? Well, I certainly feel sorry for you. Now, perhaps you noticed there was a peculiar quality in that voice you've not heard before. That was the vibrato. We noticed a little while ago that a vowel sustained without inflection didn't sound human. it sounded this way. Now, if we put vibrato into that same tone, we get this. And that, as you noticed, is really a singing tone. Yes, Voder can not only talk, but he can sing. Test your voice for us, Voder. Well, if you've quite recovered from your mood of depression of a few minutes ago, suppose you sing a song for us, will you?
Yes, certainly.
Well, how about Old Lang Syne?
Okay. She's overgrown and before I never going on. She's overgrown before I
I'm sure that if I sang that song, I would sound as good as the voter. Miss Harper, I've been wondering whether our listeners realize how many motions you have to make in the production of a single word. Can you give us some idea?
Well, for example, in producing the word concentration on the voter, I have to form 13 different sounds in succession, make 5 up and down movements of the wrist bar, and vary the position of the foot pedal from 3 to 5 times, according to what expression I want the voter to give the word. And of course, all this must be done with exactly correct timing.
About how long did it take you to become an expert in operating the voter?
It took me about a year of constant practice. This is about the average time required in most cases.
How many girls are there who can operate the voter?
The company tried out about 320 girls, and out of this number, 28 girls finally became expert operators.
Well, that seems like a very small number. Just why is that?
Answer that, Dr. Caldwell, by saying that in operating the voter, a girl needs a peculiar combination of particular talents, which is not too common.
Mr. Garrett, does the voter speak any foreign language?
Oh, yes, the voter can talk practically any language that its operator can talk.
Well, suppose we try a little French on the voter. Can he say, parlez-vous français?
Parlez-vous français?
Splendidly done.
Merci, monsieur.
You see, Doctor, the voter can do practically anything that can be done with a human voice.
Well, that certainly covers a lot of ground, Mr. Garrett. I know people who can imitate animals. Can the voter do that, too?
Oh, pretty well. For instance, here's Voder's imitation of a cow. And here's
I
a
think that's
pig.
Homer Dudley.
Have you given the voter any real education yet?
Just what do you mean by that, Dr. Caldwell?
Well, for example, does he know his alphabet?
I'll let you judge that for yourself.
Well, that certainly proves the voter's versatility. And now I'd like to ask just what to see for the voter, Mr. Garrett. How can it be practically applied?
Well, Dr. Caldwell, we don't anticipate any commercial use for the voter. It was built for an educational exhibit for the New York World's Fair and San Francisco Exposition. However, it is a byproduct of developments that we are going on and doing in the Bell Telephone Laboratory.
Will you please make the voter say for our Eastern listeners, good evening, radio audience?
Good evening, radio audience.
I think that's it. Interesting? And you can see how difficult it was for them to really make it sound like the human voice. And a lot of that's due to the circuitry that they had available at the time. They had relays, they had a buzz and a hiss. They didn't have the wave files and all of that stuff that we've got today. Even with PCM, some of those calls sounded kind of funny. Even with the stuff we've got today with the radios and the DMRs, some of the voices come through kind of different, don't they? Yeah. Yeah, and this is the legacy that it kind of comes from. Any other questions?
I was actually kind of surprised at how similar it sounds to DMR. I know there's been 90 years of progress, but it has that same voice and sound quality to it, especially if you have like a really low quality DMR vocoder in your radio.
Like a Chinese radio?
Yeah, those tend to be a lot more robotic.
Yeah. So that's all I have for you today. I think that's the limit of the class today. And if you got something out of it, we'd appreciate some feedback. Anybody else? What? Oh. Yeah, the voter.
All right, thank you, everybody. Much appreciated. If you guys have any questions, you can drop us an email, and I'm going to turn it over to Willem to close things down.
Well, thank you, everybody, for attending. Really appreciate you being here. Also, thank you to all of our presenters. It takes a tremendous amount of time to prepare for these presentations. So really appreciate all of the effort that you put in getting this presentation put together. And it was very, very interesting. And at least I learned a lot in the process. Since this is our last RMHAM University for the year, I'm wishing you the best for the holiday season, whatever holiday you may be celebrating. I hope you have a very joyous time. And our next RMHAM University is the one on 3D printing that will be presented remotely. So we won't
hope.
meet in person. Yes. We won't be meeting in person in January, but do join us for the long-awaited 3D printing RMHAM University. Our next in-person one will be NerdFest, which is in February. So if you have a short topic, somewhere in the range of 20 minutes to half an hour that you would like to talk about, we'll get the sign up here posted very shortly and send out an announcement. So we'd love to have you come and present something to the rest of the group on some nerdy topic. So hopefully we'll see you all there. Thank you very much, and we'll see you again soon.